So thanks very much, Anna Maria, for that very generous introduction, and now I have to live up to it. So before I try to live up to it and impress you, let me say right from the start, I'm going to share with you data from gravitational wave detectors that has been made possible by literally hundreds of other scientists. I want to acknowledge all my colleagues up front, and also from support from the National Science Foundation, and so many thanks to those. Now let me tell you, if you looked at posters around the building and you see that my talk title is a little different than that, it's because just under 10 days ago, we celebrated the 10th anniversary of the first detection of gravitational waves by LIGO. And so I wanted to really use this talk to tell you a little bit about how we got to that first detection and what's happened in the 10 years since. Now, some of you, the young people in the audience won't know, but for those who've heard me speak before will know this, there'll be something for everyone. If you came here to hear about quantum physics, I'll tell you a little bit about our quantum experiments. If you came here to hear about astrophysics, I'll tell you a little bit about our astrophysics. And if you came for one or the other, you'll just have to put up with the other half. Okay, so that's the layout. So let me just start with the story of how gravitational waves began, and that began with Albert Einstein in 1916 when he first came out with the theory of general relativity. And there was a time-dependent part to Einstein's field equations that turned out to be gravitational waves. And these are ripples of space-time. And Einstein himself at the time was extremely pessimistic about them. In later parts of his career, he was pessimistic about their very existence. But early on in those 1915 and 16 papers, he saw them come out of the equations, and he kind of just said, well, they'll never amount to anything useful. Okay, so that was one of the closing sentences of his original general relativity paper. Now, Einstein at the time was probably thinking about gravitational waves from ordinary stars like our sun, but it wasn't until the 1960s and 70s that neutron stars and black holes were discovered. And these are very compact astrophysical objects. And when you think about neutron stars or black holes orbiting each other, these become strong emitters of gravitational waves, whereas ordinary stars like our sun in orbit around another star just are negligible in their emission. So Einstein's sort of ambivalence was perhaps justified. But then in the late 1960s, this man, Kip Thorne, then a young professor at Caltech, told us that yes, these gravitational waves do exist. There was a lot of back and forth over the preceding 50 years about their very existence, and Kip was one of the first people to take these newly discovered neutron stars, which was in 1967, and black holes in 1971, and to start asking if they emitted gravitational waves, what would the strength of the waves be? And he gave us the first answer, which was that they would have an amplitude of a part in 10 to the minus 21. And appropriately, these are dimensionless, because one of the things that we know already from the time of Einstein is that these gravitational waves act as a strain in space-time. So they shrink and stretch space-time as they propagate through space-time, and the amount of shrinking and stretching is proportional to the space-time distance that they occupy. So that was a Thorne. And then around the same time, in the early 1970s, this man, Ray Weiss, then also a young physics professor at MIT, came up with a scheme for measuring them. And Ray's big innovation was that they are detectable. They're awfully faint, but if we can figure out how to measure changes in space-time distance of the order of 10 to the minus 18 meters, then they should be detectable. Now, on this 10th anniversary of the first discovery of gravitational waves, I've already let out the cat out of the bag for those of you who haven't been paying attention. They were discovered, but I have a few other things to say along the way, and one is that just under a month ago, Ray Weiss passed away. And he was a great giant of the field. And so I wanted to take a minute or so just to tell you about what his significant contribution was. The first thing to say is this photograph was taken just about 3 months before he passed away, and he was discussing primordial black holes. So right to the end, he was very engaged with science. Now his big innovation was that he, in 1960, in the 1960s, lasers were also invented. And he came up with the idea, along with others independently, but his big innovation was use a laser interferometer to measure these changes in space-time distance. And the recognition that if you made a laboratory scale interferometer, a meter scale interferometer, you would have to have the challenge of measuring changes in the displacements of the interferometer mirrors at the level of 10 to the minus 21 meters. Because remember, that's the changes in space-time distance from a gravitational wave of amplitude 10 to the minus 21. And he understood that that was really unfeasible. And so instead what he said is make these interferometers long. Make them 4 kilometers long, and then you have the mere task of measuring displacements at the level of 10 to the minus 18 meters. And in a 1972 internal memo, never published, this is what that picture is from, he laid out what the experiment would look like, including some of the most important noise sources that we would have to contend with. Now, in 1975, Thorne and Weiss met, and they hatched up the idea of actually building such an interferometer, not just this tabletop one of meter scale, but a full 4-kilometer long detector. And that chance meeting in 1975 turned into a many decades long collaboration, and in the late 1980s, the National Science Foundation agreed to fund the construction of the first phase of what was LIGO, or the Laser Interferometer Gravitational Wave Observatory. And it turned out to be 2 sites, one in Washington State, about 3 hours drive east of Seattle, in the high desert, and another one in Louisiana, sort of halfway between Baton Rouge and New Orleans in a pine forest. And there were sort of 2 really important things you have to do to achieve a measurement sensitivity at the level of 10 to the minus 18 meters. And the 2 things you have to do are you have to make the mirrors of your interferometer so well shielded from all the other external forces that are driving their motion that they'll respond to space-time changes in the passing gravitational wave. And to do that, in the case of LIGO, we do 2 important things, many other things. I'm going to brush over a lot of the details of the over 1,000 control loops that are involved and the 30 or so subsystems, but I want to give you the top level view of how you would build a gravitational wave detector. So the first thing you do is you create a quiet platform to mount your mirrors on, and that quiet platform turns out to be a vibration isolation system that works kind of like noise canceling headphones do. You measure displacements around your platform, and then you push back on the flat platform to cancel the motion being induced by the external forces. And that gets you to about 10 to the minus 13 meters. Now, just to sort of put a scale on this, if you did nothing, you just left mirrors sitting in a sort of ordinary room like this, the typical motions of the surfaces of the mirrors are around, at the largest scales, around a micron. So remember, to get to 10 to the minus 18 meters, you have to shield them by a factor of 1 trillion. Okay? So this vibration isolation platform gets you down to 10 to the minus 13 meters. And then the next thing you do is you hang your mirrors from a cascade of pendulums. And in the case of LIGO, these mirrors are hung as a cascade of 4 layers of pendulum. And when you do that, then you get to a sensitivity of displacement limit of about 10 to the minus 18 to 19 meters. So now you have, you've mounted your mirror. So what this picture shows is that the mirrors of LIGO, this is the actual test mass of gravity, of general relativity. And you can see above it is another stage, and then there's 2 other stages above it. So these are 4 stages of pendulum. Each stage of pendulum gives you an isolation factor that goes as 1 over the frequency squared above the resonant frequency of the system. The typical resonant frequency of this pendulum system is about 1 hertz. So you can quickly make the calculation in your head that each stage gives you isolation of f squared. So you get a factor of f to the 8th isolation from 4 stages. So if you were measuring at 100 hertz, from your 1 hertz, you have 100 to the 8th as your isolation factor. Okay? So that's essentially how you have to think of it. These are not quite as clean and pristine systems as that, but that's the way. So now you have a really still mirror. And the next challenge you have is also another factor of 1 trillion, which is how do you measure such small displacements? And in this case, the L in LIGO comes into play, which is the laser. The laser is, the wavelength of the laser light is the tick marks on our ruler for measuring these displacements. And the factor of 1 trillion comes from the fact that we have the wavelength of the laser light is a micron. It's the 1064 nanometer lasers. And now we have to measure 10 to the minus 18 meters. So another factor of 10 to the 12. And the way that we do that is by averaging over a large number of photons. So we use very high power lasers, and then we use optical cavities in the arms of LIGO. And optical cavities, for those of you who are not familiar, are basically 2 mirrors facing each other. And just as if you put your own head between 2 mirrors and you see multiple reflections, the laser light bounces multiple times, and that it has a resonant enhancement for the light. And between those 2 effects, you can get a very large number of photons involved in the measurement, and then you average over those large number of photons, and that gets you to that factor of 1 trillion in sensitivity that you're looking for from the measurement. So and then this was funded by the National Science Foundation since the 1970s, and it was approved for construction in 1989. And this man, Barry Barish, is credited with being responsible for getting these observatories built and the technology set up to scale. Okay. Now, the 2 LIGO detectors are part of a global network of detectors. There's the 2 LIGO detectors in the United States. There's a 3-kilometer-long detector in Italy called Virgo. There is a 3-kilometer detector in Japan called Kagra. There is under construction a 4-kilometer replica of the LIGO detectors in India. And then there is also an approved mission called LISA for a space observatory, a space detector. So that's the global network. And now we fast forward to 2015. So these detectors were built. I've told you a little bit about the principles of the measurement. And we fast forward to 2015, and that was the first detection of gravitational waves. This is the iconic GW, stands for gravitational wave. 15 is the year 2015, 09 is the month September, and 14 is the day. So you can see we're really just 10 years out. And this was the signal measured in the 2 LIGO detectors. And there's a few things to notice here that are important. The first is that this is a signal from 2 black holes that orbit each other, and they've orbited each other for billion years or so, and we catch the last 200 or so milliseconds of their lifetime before they collide. And they collide because these systems are strongly radiating gravitational waves. Those gravitational waves carry away energy. That energy comes out of the orbit, and they collide. Now, at the moment of the collision, which is the maximum amplitude here, the gravitational wave amplitude was 10 to the minus 21. It's a big check mark for Kip Thorne. He told us in the late 1960s that it would be so. Now, if you ask how much the the mirrors of LIGO were being displaced at this moment. It is 4 times 10 to the minus 18 meters, big check mark for Ray Weiss. He also told us in 1972 that it would be so, and he told us how to build the instruments that would be capable of doing so. And the properties of the system were that these happened to be two black holes that were about 30 times the mass of our sun. At the time that they collided, they were moving at half the speed of light. So this is something you should really take pause to contemplate. You have things that are objects that are 30 times the mass of our sun that are moving at half the speed of light. They were about 1.3 billion light years away, and in the collision of these two black holes, 3 times the mass of our sun was radiated away as gravitational waves. Okay, quite an extreme system. Yeah, so the way that we actually know about these things is that the Einstein's field equations, you can solve them they're actually quite difficult nonlinear equations, but you can solve them in a few exact cases. And they encode all of the properties of the object. So for example, this is a chirp. It doesn't look like this because these data were early data, but this is a chirp, and by looking at the frequency evolution of the signal, so the frequency is a function of time, you can extract the masses. Once you know the masses of the system from the frequency evolution, from the amplitude, you can extract the distance. So that's an example. And some of these parameters are, so if this if this chirp were modulated, then you would be able to extract the spins of the black holes from that.
No, but I guess I was getting at, from the LIGO experiment, is the strain coming from interference of photons? You didn't talk about it.
Yes. Yeah. So the signal itself is the output of the interferometer. The interferometer, what it does is it splits the laser beam. The laser beam goes towards the two end mirrors, reflects, comes back, and at the beam splitter, it can either destructively or constructively interfere based on the path length differences. And so the amount of light coming out at the output port is a measure of the path length difference, and that's the measurement. So the measurement is actually photodetection. And I'll tell you a very cute anecdote. I was working on one of these interferometers, and Kip Thorne came by. And I was showing him around, and I showed him the actual photodetector where the measurement is made at the output of the interferometer. And I said, that is there's your gravitational wave signal. And he was quite offended, because for him, the gravitational wave signal was the motion of the test mass itself. So for him, the true object of general relativity was the test mass. He's right. But for me, as an experimentalist, that transduction from the mirror motion to light was the only measurable thing that we had. So that's that's the question. Okay, so for this discovery, these 3 gentlemen won the Nobel Prize in 2017. And it was the Nobel Committee called it a discovery that shook the world, and it was very significant at the time. But what I really want to talk about is that I titled my talk "Opening a New Window to the Universe," and one, sort of monumental discovery or event, astrophysical event, does not a window to the universe open. That's one event. So what I want to do is I want to sort of talk to you a little bit about what we've seen since then. So in the 10 years that have come since then, we have seen something that's on the order of 300 astrophysical events. And the way that advanced LIGO works is it's designed to have periods of scientific observation called observing runs, and then periods when we take the instrument offline to do instrumental improvements. And so the first observing run, in which the first discovery was made, and that object on the left is the very first one, we saw 3 confirmed events. In observing run 2, we saw something more like 8. In observing run 3, we saw a lot more. And then in observing run 4, which is still ongoing, you can see that we've seen. And this is not all 3 events. This is just a catalog of the first 200 or so events. There's many more. I mean, but I just wanted to give you a sense of, and what each of these pictures shows is a time frequency spectrogram of the event. And so you can see anytime you see a chirp like this where the signal is growing in time and frequency, that is some kind of binary coalescence. And I will say, so I'm going to spend the next 5 or so minutes on some really cool astrophysics that has come out of this in the last 10 years since that first discovery. And the next really big thing after the very first discovery of black holes was the discovery of a pair of neutron stars that collide. And this, you can see, comes, this is an event called GW 170817, so it was in 2017. And you see something that's intrinsically different. The black hole event that I showed you had a time scale of under a second. Remember, it was 200 milliseconds. This signal lasted in our detector for over a minute. And that immediately told us that it's a much lighter object. That's just and indeed, what we then saw was about 1.7 seconds after the LIGO registered this signal, the Fermi Gamma Ray Observatory also saw a large trigger. And so now the thing that's special about neutrons, the black holes are purely gravitational objects. When black holes orbit each other, all you see is gravitational waves. When black holes collide, all you see is gravitational waves. There's really no expectation of light being emitted, except if the black hole happens to be in some field of matter and it sucks up the matter and radiates, but otherwise not. Neutron stars are really quite different. When they're orbiting each other, you see gravitational waves radiated, but when they collide, it's like a neutron collider, and you should see a very spectacular light show. Now, at the time that the LIGO signals were detected, we could, because they were detected in 2 LIGO detectors and not detected by Virgo, you could use triangulation to say what patch of sky they were in. And that patch of sky happened to be pointing in the southern hemisphere, and at the time of this signal, it was daytime in the southern hemisphere. So an alert went out to the astronomy community, and astronomers had about 11 hours to prepare their telescopes to go look for this object. And then came an astronomer's night to remember, very busy plot, but I just want to give you a sort of a sense of this. So we saw the gravitational wave signal, and then in every band that we looked in, we saw signals in gamma rays, in X-rays, in UV, optical, IR, radio telescopes. Everybody saw an electromagnetic counterpart. I'll just point you to an optical telescope. So here's a whole bunch of optical telescopes, and you can see they're all pointing at a galaxy called NGC 4993. And in every crosshair is there's a little object at the outskirts of that galaxy. Now take this telescope, DLT 40, and let's look at what it saw in the same field 20 days earlier. There's nothing there. So this was a new object that lit up in the sky, and this is very consistent with this picture of neutron stars, which basically says whilst they're orbiting each other, you see nothing but gravitational waves, and then eventually when they collide, you shall see at first a big, very beamed gamma rays, and then after that you see all different colors of light given off by the debris. Okay? And so that was essentially, this object is called a kilonova. It was just about 10 years before this discovery. It had been theoretically predicted, and that's what we saw. Now, there's one other thing that we saw that was very interesting. You can also do spectroscopy with the optical signals. And in doing the spectroscopy, you can see these are just number of days that are I don't know why it won't play, but that's okay. Yeah, as the number of days goes by, you see the spectrum changing dramatically. And what we were seeing in this spectrum was the formation of heavy elements, and in particular heavy elements like gold and platinum. So there's long been a mystery here on the Earth that we have too much gold and platinum and the lanthanide and actinide seas. And you might say, well, what does too much mean? So we know that elements are formed in stars like our own sun, but those kinds of stars can only fuse elements up to about iron. If you want to go heavier than iron, then you can think about supernovae. That's the next object in which you have enough of a neutron-rich environment to fuse heavier elements. But that doesn't get you all the way either. And so it had been posited that these heaviest elements like gold and platinum and the lanthanide series and the actinide series must be formed when neutron stars collide. And these spectra were the first observations of that. And so I'll just point you to this a periodic table here, and what you see is that the yellowed out elements are, according to their proportions, what we saw being formed in neutron stars. So in that single observation and the spectroscopy that followed, we were able to explain the abundances that we see of these heavy elements here on the Earth. And that's something remarkable about our own history, because what it says is that sometime in the history of this location of the solar system, there must have been a neutron star collision. Okay? So that's some of the science that came out of the neutron stars. Now I'm going to just spend a couple of minutes telling you about just a handful of some of the most intriguing objects that we've seen. And then we end the astrophysics part. So for those of you who are waiting for quantum, it's coming. All right. Okay, so we saw an object, 1908-14, that creates a new mystery. Now, what we know from the way that stars collapse is that if a star is about a solar mass, or up to about 1.5 solar masses, as the star collapses, it will collapse into a neutron star. If the star is about 5 solar masses or more, the parent star when it goes supernova, it will collapse all the way to a black hole. And there is this mystery which is called the lower mass gap, where we don't expect or know what to expect just from the way that the dynamics of these systems work, if you could form an object that's in between. And here we saw for the first time an object that was in between this 1.5 solar mass and 3 to 4 solar masses. And is it a neutron star or is it a black hole? We don't know. But what we do know is that we don't know the mechanism by which they're created, but it does look like nature does create them. Okay, so that was one interesting thing. The next interesting thing that we saw was this object, GW 231123, and this are objects that are in something called the upper mass gap. Now, the upper mass gap is that between about 60 solar masses and about 150 solar masses, we also don't expect these stellar collapse black holes, and for a different reason. And the reason is that for stars that grow that massive, pair production in their cores actually causes them to have a runaway thermonuclear reaction, and they should just explode and blow off. And there should be no remnant left that collapses. And yet we see that. So that was another very interesting object. And the other thing that was interesting about these objects was that these black holes we could see were maximally spinning. Point one is the highest a black hole can spin. And these are very close to maximum. And this has set off a very interesting set of calculations and inquiry into this idea that then these black holes mustn't form at this mass range, can't form from stars, and so they must be hierarchically assembled. So lighter black holes, merge, and then we found, another pair merge, and this also presents astrophysical headaches, because then what it says is you have to be in some kind of astrophysical region where you have enough of these black holes that they find each other hierarchically to keep merging. And so that again is new questions that are coming up. The last object that I'll tell you about is one called just from earlier this year, in January of this year, and this is the loudest black hole system we've seen. So highest signal to noise ratio system. Very interestingly, almost identical in its properties to that very first one that was 10 years ago, but now we have instruments that are about 3 times as sensitive. So we have made sensitivity improvements by about a factor of 3, and that lets you do much more precision measurements. And among the things that we could see by being able to see the number of cycles until the collision, and in particular the number of cycles of oscillation after the merger, you could learn a few things. One was we have now, for the first time, being able to test the no-hair theorem of general relativity, which basically says that black holes have no hair. They are perfectly described just by their mass and their spin and charge, but nobody ever really cares about charge because it's expected to be 0. So you were able to actually measure that these black holes with these properties are mathematically identical to what you would predict from a no-hair black hole. The other thing that was able to be done was to test the area theorem of Stephen Hawking. And what Hawking told us in 1971, I think, that the area of a black hole event horizon cannot shrink. Now, the event horizon of a black hole, just thermodynamically, is an information shielding surface. And so if the event horizon of a black hole were to shrink, it would mean that the entropy of the system is decreasing. And we were able to measure with very high precision that the areas of the two parent black holes was, in fact, smaller than the area of the newly formed black hole. So thermodynamics is also alive and well. Okay, now I want to tell you about, I want to show you one other thing, which is just amazing. So I just want to show you the two signals, the original one. Now these two systems, 25, the one from earlier this year, like I said, very identical. 30 solar masses, about 1.1 billion light years away. But now you can see the quality of the signal, and therefore the modeling that we can do. That's and this is now what I want to spend the rest of my talk on, which is these didn't just come from nowhere. This comes from years of improving the instrument sensitivity. So just to give you an idea, this one was detected with a signal-to-noise ratio of 26. The one earlier this year was a signal-to-noise ratio of 80. Okay, so how do we do this? To talk about improving detector sensitivity, I should say a little bit about what limits the sensitivity of the detector. And so I'll start just by showing you a couple of plots. So on the right side is the cumulative detection rate for astrophysical events. O1, O2 simply refers to observing run 1, observing run 2. Observing run 3 and 4 were broken up into two parts with a break in between for instrument improvements. And you can see that the slopes of these things are just getting higher as we make detector improvements. Now on the left side are a way that we take snapshots of the instrument sensitivity. So on the vertical scale, we have the spectral density of the gravitational wave strain. And on the horizontal scale axis is the frequency of the gravitational wave we might be able to measure. The green curve is the performance of LIGO in its first phase, which ran from 2000 to 2010. The red curves are the advanced LIGO sensitivity during observing run 1, when those first detections were made. The blue and the cyan curves are the target sensitivity for advanced LIGO, and then the cyan curve is actually an upgrade that we had planned. And I'm going to just walk you through a little bit of what are the technologies that were involved in this. Yeah, I can comment on the spikes. So these spikes there are largely three things in there. The ones at 60, 120, 180, these are power lines. Okay, and if you went to the European detector, they would be at 50, 100, 150. So so that's just the power lines. The family of spikes over here are to do with the mechanical resonances of the fibers from which the mirrors hang. Remember, the mirrors hang as pendulums. The fibers that support the mirrors are under tension. And so these are the frequencies at which those fibers twang, like if you twang a guitar string. Now, we don't intentionally twang the guitar string. The thermally driven fluctuations are twanging them. So that's that. And then almost all the others are calibration lines that we put in. And they look rather horrific on a scale like this. They are actually less than a bin wide, and so they're very easy to remove in the data when we're doing the analysis. Okay, now what makes up the sensitivity? So this is a busy plot. I only want to point out a couple of things here. The black curve is the target sensitivity of advanced LIGO, and you can see sort of 10 hertz to a few kilohertz is the range in which we plot this curve. The magenta curve under it is the quantum noise, and that's the thing I'm going to focus on for the rest of my talk. One thing to notice is the red curve, which is called the coding Brownian noise. That's the thermally driven fluctuations of the mirror surfaces. And that is, as a lot of my quantum optomechanics friends here know, this is the most vexing of problems when you want to make a quantum limited measurement, is that the thermal noise, the classical the thermally driven fluctuations, are the ones that get in the way. Now I'll say one other thing for those of you who like such things, which is that there is a noise source here, the green curve, Newtonian noise. This is a noise due to the fact that these suspended mirrors get shaken about by small fluctuations in local gravity that may occur by clouds passing overhead or a seismic wave running deep underground near the test mass. And that is a noise source, as you can see, that gets worse dramatically as you go to lower frequencies. And that is the reason you would ever want a LISA. That is the reason you want a space detector, because on the Earth, we are limited by this Newtonian noise, and technological solutions that we know of don't really get us beyond a hertz. So if you want to measure lower frequency gravitational waves, the space detector is your answer. Now, what is this magenta curve, the quantum noise, made up of? It's got two parts to it. On the high frequency end, just above about 100 hertz, it comes about because of the limits to the uncertainty in the number of photons we measure on our detector. So I told you our measurement is actually the light coming out of the interferometer, and the quantum fluctuations on that light give us the shot noise limit. And here the temptation would be, it's a Poisson distributed noise source, so your temptation would be use more laser power, because then your signal to noise will scale as the square root of the laser power, and you can do better. Now, in the case of LIGO, our mirrors are by design movable. And what happens is, as you increase the laser power, the radiation pressure noise, just those same fluctuating number of photons that are giving us the shot noise, are going to apply momentum kicks to our mirror. And as you increase the power, more momentum kicks, and that then gives us on this side this radiation pressure noise. So on the one hand, we're tempted to increase the power, and that will give us a stronger measurement. But then from that, we also get a larger back action. The process of measuring the mirror motion actually kicks the mirror. Okay? So what can we do about that? Well, in the early 1980s, Carl Caves already gave us a solution. He said a key requirement would be to inject squeeze states of light into the unused port of the interferometer. So let me just talk a little bit about what that looks like. So you take a toy interferometer, and you inject a laser light beam into that. The light reflects off the mirror, and you can arrange these two path lengths such that no light comes out at the output port. And that means that all of the noise and fluctuations of the laser, classical or otherwise, will just reflect back towards the laser, because no light comes out here, and therefore no laser noise. If no laser light comes out, no laser noise can come out. But quantum optics tells us that this is an open port through which vacuum fluctuations will enter the interferometer. And the same symmetry of the beam splitter that makes all the laser light go back towards the laser will cause any field coming in this port to come back out this port. So now, if you have some path length difference, and you make a measurement at the output here, you get a little bit of coherent field from the fact that your gravitational wave may have caused some of your laser light to come out. And that superposes with these vacuum fluctuations, which are represented in phase space as this minimum uncertainty source, where you have, quantum mechanics forbids you from knowing with perfect precision what the amplitude and the phase of your light are simultaneously. Okay, so if you now measure at the output, what you will see is your signal phasor superposed on this vacuum state or quantum uncertainty, and therefore you can't know the length of your phasor perfectly well, and that gives rise to the shot noise. And that's the picture Cave set up for us. Now, by the very same vacuum fluctuations, also superposed with the bright field at the mirrors, and those vacuum fluctuations are then kicking the positions of the mirrors. Okay? And that gives rise to the radiation pressure noise. So what if you could then, instead of ordinary vacuum states, inject a squeezed vacuum state? So what does a squeezed vacuum state look like? It looks like this. If you inject this squeezed vacuum state in here, now it's very carefully engineered so that now, so what is a squeeze state? So a squeeze state is one in which you can reapportion the noise so that you can make the noise much better in one quadrature, in this case the x2 quadrature or the phase quadrature where we're making our measurement. But if you are to not violate Heisenberg's uncertainty principle, you have to increase the noise in the orthogonal quadrature such that the product of the variances of these two noises doesn't violate Heisenberg. So we carefully can engineer a vacuum state so that it's squeezed along our measurement phasor, and then these two superpose, and you'll make a measurement that's more precise, that has better signal to noise than if an ordinary vacuum state was entering. And that's, Caves told us that in the early 1980s. So now fast forward to the year 2019 is when the paper was published. We started working on this many years before, but this was the first time we were able to inject squeeze light into the LIGO, advanced LIGO detector during observing run 3. Now, without much detail, I'm just going to show you, here is the interferometer, and here is the main laser, and this is the output where we would normally measure the gravitational wave signal. And what we did was we then introduced a squeezed vacuum source. We coupled that squeezed vacuum into the interferometer, and then we were able to make the following measurement. So the black curve here is what you get as the sensitivity of the instrument when you don't have squeezing. And then the green curve is what we were able to measure when you injected this squeeze state into the interferometer. And you can see not just the sensitivity improvement, but what this amounted to. This was most of, but not the only improvement we did between observing run 2 and 3. But we went to measuring 5 astrophysical events per month with these improvements compared to 1 per month in the previous 2 observing runs. So when you ask, now, what do we do? These are the kinds of improvements we do to increase our detection rate. So that was the first use of this quantum engineered light, these squeeze states of light, as Anna Maria pointed out, to seek quantum advantage. Okay? And this improvement was about 3 dB or 30%. Okay, now notice something here. At this point here, the green curve goes above the black curve, and I can show you that in an even more pronounced way over here. So what is going on there? And what's going on there is that, remember, at low frequencies where we become sensitive to the radiation pressure noise, right? And so here what's happening is that our sensitivity is being destroyed by the long part of the ellipse, okay? And so now what we would really like to do is to be able to address that. What is going on there in this region is also something that Caves told us about again in the early 1980s, and that was that these quantum mechanical radiation fluctuations disturb the measurement. So that's what we're seeing, okay? Okay, I'm glad you all noticed what a fabulous abstract this is, okay? Yeah. Okay. All right, right, so now I want to take you to a third very important thing that happened in the field, and that was right around 2001. This paper came out with a cast of authors, including the late Jeff Kimball, that led the way for us to start thinking about how we may make improvements to these gravitational wave detectors using quantum technologies. And so there were three things that I want to point out in this paper, and all three things I'll show you systematically we then have measured. So the first one was, so this is their version of frequency of the gravitational wave versus the spectral density of strain in some units where they have normalized it to something called the SQL. And in this case, the SQL is the standard quantum limit. Now, I will just say every field has its own standard quantum limit, so it is not standard. And as you will see, we can surpass the standard quantum limit, so it's not a limit. But so what I think of it as is it's a benchmark. And what is this a benchmark of? In this case, it's a benchmark of something quite beautiful and fundamental. It says if you measure the position of a particle using light, how well can you do? So I've already told you what the conundrum is. On the one hand, you want to use more photons so you can better resolve your fringe and make the measurement. On the other hand, using more photons, then the radiation pressure from those photons kicks your particle. And that's the balance here. So what they told us was you can do three things. You can inject squeeze light at a fixed squeeze angle, and I'll show you that's what we already did. Then they said, well, if you really want to do better, you have to do this curve, which is to inject squeeze, what they call squeeze input is when you can actually make squeezing frequency dependent, and I'll tell you in a minute what that is. And then the third thing they told us is if you can exploit quantum mechanical correlations inside your interferometer, then you can do even better. You can start to do these kinds of shaped responses. So let me show you what these are. So the first thing I want to say is I want to introduce one other idea, which is optomechanical squeezing. So the squeezing I've shown you so far is done using nonlinear optical materials. And one way that you can think about squeeze sources is what squeezing does is it correlates amplitude and phase. Okay? It's a bit heuristic, but it works well for colloquia. Okay. So what happens here, take an optomechanical system like this, where one mirror of your optomechanical system is movable, and now here's what happens. So here's your coherent field, and here's your quantum fluctuations on it. This light hits this mirror, and so here it has some fluctuations in the amplitude or the number of photons. And that provides a force on this mirror. The force causes the mirror to displace, and the displacement of that mirror causes a phase shift in the light that's reflected. And that process together can correlate your phase and amplitude fluctuations, and that should result in a squeeze state. Now, what you'll see is I'm just going to give you an experiment where we actually did this. So here's an experiment where we had this little optomechanical cavity where this was a little 100 micron size mirror, and we actually coupled strongly to this radiation pressure. So we drove the mirror positions with this quantum noise limited light. And what we were able to see, I won't give you the details of it, but here you see that we were able to observe a squeeze state. So how do you know this is a squeeze state? Here is frequency, and the blue line is the shot noise limit. It's if you had pure vacuum fluctuations. And then when you have squeeze vacuum, you go below that level. Okay, just as you saw with the other interferometer. Now, I will say something very fun about this measurement, which is that the original pun-remoted squeezing measurement was done here in Cindy Riegel's group, and we were just following suit in frequency ranges that were important for gravitational wave detectors. But this establishes that this phenomenon happens. This radiation pressure coupling to a movable mirror squeezes the light. And now we're going to use that. So the first thing that measurement that we did was we went to that 2001 paper by Kimball et al. And we said, can we actually go below the standard quantum limit in this case where we have squeezing that's the same at all frequencies? And indeed, what we were able to do was to show by subtracting out the classical noise. Remember, at this point in LIGO, our classical noise was larger than the quantum noise in some bands. So by subtracting out the classical noise, which we know how to estimate because we know how to estimate the quantum noise, we were able to show that indeed you can arrange the interferometer readout such that you can go below the standard quantum limit, just as they had shown us. And in fact, in this case, this the dark dashed line is the standard quantum limit, and the light line is 3 dB below that. And so what this tells us is that by injecting squeezing into the interferometer and by using the shearing of the interferometer, the rotation that the interferometer makes off the light field, you can actually use those correlations inside the interferometer combined with the squeezing, and at a certain frequency you can make your sensitivity very good, below the standard quantum limit. Now, this wasn't used in a gravitational wave observation because you could see the gray curve, the brown curve, the classical noise was still above this. But it told you that the quantum noise in the system can go below the standard quantum limit. It's not dependent on frequency. So what this one was that the squeezing that we inject into the interferometer is the same. The rotation, the orientation of the ellipse is the same for all frequencies. Now what's creating this effect is that once you get inside the interferometer itself, through that radiation pressure coupling, is shearing and rotating your ellipse. Okay, so what it's doing is it's using the correlations in the interferometer. It's an additional, it's a squeezing upon a squeezing, yes.
So in that sense, that, because I was thinking you can optimize the angle, but then you would have to optimize for a given frequency. Exactly, that's the rub. Look, if I had a source right here at 40 hertz, fabulous. I would make this green curve and operate there. The fact is, for discovery, we need a wide band. And so what are we going to do? And you set me up perfectly. What we have to do is we have to then go to this curve that Kimball et al. Told us about. And to do that, we have to do one additional trick, which is we have to take this squeezing ellipse and we have to rotate it as a function of frequency so it's optimal at every frequency. So let me just show you how that looks. So this is a toy of, the blue curve is the advanced LIGO sensitivity without squeezing. And then the red curve is if we put in frequency independent squeezing, which means the squeezing ellipse is the same at every frequency. And what you see is exactly as expected. Our squeezing ellipse was oriented such that the shot noise would get better, but then we're probing the long part of the ellipse for radiation pressure, and it makes things worse. Okay, so if we could create a squeeze light source where we had a squeezing orientation like this at high frequencies and squeezing orientation like this at low frequencies and everything in between in the in-between frequencies, then we could create this broadband black curve. So of course we're going to do that. Now I'm going to very quickly just cut to what we did. So the way you do this is an optical cavity has a frequency-dependent phase shift because it's a resonator. And so what we do is we take our squeeze state and we reflect it off an optical cavity, and that reflection then is a frequency-dependent rotation of the squeeze state. So that's conceptually straightforward. For those who follow and for those who don't, it's what we do. Now the thing that's really difficult is why do we need this rotation in the first place? We need this rotation because LIGO has 4-kilometer-long optical cavities that are also frequency-dependent phase shift, and it's the action of those optical cavities that is causing this shot noise, radiation pressure noise rotation in the first place. So the easy thing to do would be to take your squeeze state that you're injecting into the interferometer, reflect it off another 4-kilometer-long cavity, and undo what the LIGO cavity does. This is a problem. 4-kilometer-long cavity, where are we going to get such a thing? So instead, we built a 300-meter cavity. So LIGO has acquired a little appendage running along the main 4-kilometer-long cavity. There it is. We reflect the squeeze field off this 300-meter-long cavity. And why 300 meters versus 4 kilometers?
Well, we can make a 300-meter cavity with low enough optical losses so that the line width of that cavity is the same as LIGO's 4-kilometer long cavity. So it's a shorter cavity, better mirrors. If we could get still better mirrors, we would have made it 100 meters or 50 meters or 2 meters. It's limited by the quality of the mirrors. So what's the line width of the light stored in the cavity? But once you do that, here's the result. Black curve is when you have no squeezing. Green curve is when you put in frequency-independent squeezing, which is the curve I showed you earlier with some other improvements. And then the magenta curve is what you get when you take that frequency-independent squeezing, first reflected off this 300-meter cavity, and then inject it into your interferometer, and you recover the sensitivity loss due to that radiation pressure. And then we can also ask, well, how is this instrument performing relative to the standard quantum limit? And indeed, what we should see is that we should see this hatched out region here. And indeed, we make the same measurement. We subtract out the classical noise, and then we measure, and again, the red curve is the standard quantum limit, and the instrument is now in a broadband way operating below the standard quantum limit. So I think that's the thing that I think is really amazing to think about in this case is we inject squeezing, and then we also use the quantum correlations inside the interferometer, and the combination of those two things can be carefully tuned to give you this improvement. Okay, that's what we're doing. Okay, I'm going to skip history in the interest of time. And I'm just going to tell you about two quick things. So we're also now starting to think about squeezing in applications beyond gravitational-wave detectors as a means of acquiring quantum advantage. And so the one thing I want to, this is actually an advertisement. So Hudson Laughlin is a grad student in my group, and he's coming to Boulder on November 3rd. And I encourage you to go to his talk, because he's going to talk about a way in which we can use two squeezed beams carefully arranged at the input to the two inputs of an interferometer, in this case a Mach center interferometer. And then if you carefully arrange the measurement at the two outputs, you can make a measurement that scales, has a Heisenberg scaling. So normally when you think about, which is sort of the ultimate limit of quantum measurement, so normally when you think of a shot noise limited measurement, I told you that goes as the square root of the number of photons in your measurement. Heisenberg scaling is when your measurement would go as n, the number of photons. So it's a more precise measurement. So I wanted to advertise that. The second experiment that I wanted to tell you about is we're also thinking about doing, we are doing making squeezers on chips, and that's just another direction in which we're trying to take these technologies that we developed for LIGO and get them out and deployed in the field. So looking to the future, we have LIGO India that's approved and under construction in India. We have two other exciting things on the horizon, which are third-generation gravitational-wave detectors. The US one is called Cosmic Explorer. The European one is called the Einstein Telescope. And one of the knobs that hasn't been turned in 50 years that we want to turn now with these detectors is to make them longer. And so these are being designed, in the case of the US detector, 40 kilometers long. And in the case of the European detector, 10 kilometers long, but in a triangular configuration. And each has advantages and disadvantages. And then, of course, LISA is under construction. Largely, NASA got out of it a decade or so ago. So it's largely a European Space Agency project. So these are the things that are coming. And so let me just close by telling you that these gravitational-wave detectors are also exquisite quantum sensors. This is just a representative schematic of how we're driving the sensitivity of these detectors down. And in doing so, in any one of these curves, quantum technologies that I described are a critical part of it, and they'll be deployed in current and future detectors. The planning of these future detectors is in full